For problem number 1 on the quiz, I give you a chemical reaction. It's the neutralization of potassium hydroxide with sulfuric acid, an acid-base reaction. And I ask you how much of the potassium sulfate we can make. I'll edit the actual question into this, but for the question, I give you an amount of the KOH and I give you an amount of the sulfuric acid. I tell you it's 100% yield. The only way to solve this is by doing a limiting reagent problem, which means you're going to have to do a minimum of 2 calculations. And without a doubt, the easiest mistake to make is to try and combine the problem into one equation, and that just won't work. So, based on this problem, I have a volume of KOH. I have 180 milliliters of a 0.217 molar solution. And so the way to approach that, right, is first we're trying to solve for grams of potassium hydroxide. Give myself enough room. And, well, what do we start with? Well, we have 185 milliliters of the potassium hydroxide solution. We have molarity, but molarity is in moles per liter. So we need to do a unit conversion. So 1,000 milliliters is equivalent to 1 liter. So we sneak that in there. Milliliters cancel. Now we can use molarity. So 0.217 moles of KOH over 1 liter for molarity. Now we have moles of KOH. Well, we're trying to get to grams of potassium sulfate, but we have a 2 to 1 molar ratio between them. So that's what we're going to use next. So 2 moles of KOH is equivalent to 1 mole of potassium sulfate. Writing it condensed to fit it on the board. Moles of KOH cancel. Now we have moles of potassium sulfate. We're almost there. We want grams of potassium sulfate. So 1 mole of potassium sulfate is 147.3 grams of potassium sulfate. Moles cancel. Now we have grams. And when you do the math, you get 3.50 grams of potassium sulfate. However, we don't know if that's the correct value because we've been given an amount of sulfuric acid. So now what we have to do is ignore this first problem that we just solved and redo the calculation for the sulfuric acid. The smallest number will be correct. That will be our limiting reagent. Okay? If you stop here, you're flipping a coin. Maybe it's the correct answer, maybe not. And that becomes obviously more problematic if you have 3 reactants, because then it's a 1/3 chance. So obviously you don't want to try that. So now we're going to set this up exactly the same way. Grams of potassium sulfate. But now we start with 115 milliliters of H2SO4. We need to do a milliliter to liter conversion. Okay? And you're given the molarity of the sulfuric acid, 0.194 molar. So 1 liter, 0.194 moles of the sulfuric acid. Liters cancel. Now we're in moles of sulfuric acid. And notice in this case, it is a 1-to-1 ratio. So 1 mole of H2SO4 is equivalent to 1 mole of potassium sulfate. Moles of sulfuric acid cancel, and notice the last relationship is going to be the same because we're solving for the same thing. So 1 mole of potassium sulfate is 174.3 grams potassium sulfate. And when you solve this, you end up with 3.89 grams. Okay. These values obviously are very, very close, but that's our correct answer. The smallest value is going to represent the correct answer because we run out of potassium hydroxide. So potassium hydroxide is our limiting reagent. Okay. So on quiz number 3, problem 2, we have a block of aluminum that weighs 475 grams. It's at an initial temperature of 215 degrees Celsius. It releases 7.18 times 10 to the 4th joules. And the question is, what's the final temperature? In this equation, well, or I should say in this problem, we're given the heat capacity of aluminum, and we're also given the equation for calculating heat. Q equals m delta T times the specific heat capacity. Without a doubt, the easiest thing to make a mistake for this problem is not realizing that when we say that it releases this amount of energy, that Q is negative. So when you set this up, we have negative 7.18 times 10 to the 4th joules equals 475 grams of aluminum times T final minus T initial, but we know what T initial is, right? So we can just put that in. Times the specific heat capacity. Okay. So right here is what we're solving for, TF. But if you forget that negative sign, when you rearrange and solve this problem, you're going to get the wrong answer. What you'll actually observe is that the temperature is going up. So I'm not going to do the painful algebra. It'd be painful to watch me do this. When we rearrange and solve for the final temperature, it's positive 47 degrees Celsius. If you get that sign wrong, that's going to give you a temperature, I think it was like 240 or something like that.